Thank you, Francis, for the nice introduction. And also thanks to all of my collaborators and mentors for working on this project. So in this project, we are focusing on telemetry data retention problem. So first, what is telemetry data? Here is one example of a network telemetry data. So it can include some 5-tuple information and also some flow-level statistics. And the network telemetry data, they are used everywhere. For example, they can be used for security diagnostic tasks or like planning tasks in your network. So with the telemetry data, here is currently how we are collecting them and using them. So let's say we collect the raw telemetry data from the devices, and then we save them in some third-party platforms like Azure, AWS for long-term retention. And then as a network or cloud operator, we want to send the queries to where the data is stored and expect some query results. However, there are three types of pain points exist in this loop. First, now the privacy regulation is becoming more and more strict. And for example, with the GDPR policy from Europe, they require that any data that could infer the user pattern cannot be saved over 30 days. And second, that for the cloud storage part, that we really want to minimize the storage cost, because when the data is generated a lot over time, then the accumulative storage cost can still be high. And third, for the operators, they really care about high data fidelity. They want high accuracy for the query they care about. Therefore, there are two types of trade-offs in this loop. First is, if you care about privacy, then you may need to add noise into your data set, and that really affects your data fidelity. And second is, if you want to minimize your compression cost, you want to minimize compression size, then that will also degrade your data fidelity. So let's first look at what is the privacy and fidelity model that we are using here. So with privacy, we are using the differential privacy, which is a widely adopted standard in industry. Here, epsilon differential privacy, they means that the released result should look almost the same, whether any one specific item is included or removed from the data set. So that an attacker cannot confidently tell whether a specific item is in the data set. And here, this privacy budget epsilon, it controls the protection. Means a smaller epsilon will have stronger privacy, but that also means that it usually adds more noise and like satisfies your utility more. So here, our privacy metric is with the same differential privacy budget, we want to optimize for the fidelity. And then for the fidelity model, we use three types of metrics. So first is a general statistic summary. For example, with your original data and the stored data, we want to check what is the statistical distance between the raw data and the saved data for each feature. And second, we also check some domain-specific queries. And third, we also want to support downstream tasks. However, because we are considering privacy in this case, that we do have some queries that we cannot support. So for example, with the aggregation query or like some general trend or pattern detection, then yes, we can support that. But because of the noise are added in the data, so if you care about some like exact flow or exact ID, you want to trace it back, then it's like impossible in this way. And also we cannot support some stateful queries in this use case. And in terms of data retention, that there are existing prior works. The first types of work are the lossless compression. You're probably very familiar with this. So currently, let's say you use gzip or 7-zip to compress your original telemetry data. The problem with this is the storage size of your lossless compression will grow linearly based on your telemetry data size. And also now, if you think of you store, let's say, 1 terabytes of data over a long time, let's say 5 years, if you want some like long data retention queries on it. And then the dollar cost of saving this gzip compressed data also grows linearly over time. And so let's say with 1 terabytes, it costs $400. And you might think that's not that many. But what if you have a cumulative cost of this much data generated every week over time? So we did an estimation that, let's say you have 1 petabyte of data generated per week, and you want to save them for over a year, then the storage cost itself can even reach over $1 million if you count the existing cloud platforms. So therefore, with lossless compression, it gives you 100% accuracy, but first, it is not private, so it doesn't satisfy the requirement, and it can also have a high retention cost over time. And the second types of prior work is sketches. So with sketches, that instead of saving the original input telemetry data, you save these compact statistics for some predefined queries. So for example, you can save for count sketch, frequency sketch, or cardinality sketch. However, the problem here is sketches are very efficient, but they are only good for the queries that you choose ahead of time. So if there's any new undefined queries in the downstream that you want to ask about, then your predefined sketches may not support those tasks. And furthermore, in terms of privacy, that for currently, if you want to add privacy into a sketch algorithm, it requires you to redesign this sketch algorithm with differential privacy, and specifically to every algorithm. And therefore, it's also unclear that what is the fidelity and utility trade-off there. And the third type of prior work is people have used deep generative models for this intention. So with input telemetry data, instead of saving the data, they learn this generative model. For example, it can be a GAN model or a diffusion model, and then they save the model for the long-term retention. And then at the query time, you use this learned model to regenerate the synthetic data and then answer to different types of queries. And with deep generative model, if you don't consider privacy, then they indeed show some good accuracy. However, with prior work, when they consider privacy, while the standard way of using differential privacy in this case is they add noise into model training. And we find out that the adding noise part really degraded the query accuracy. And also, in terms of cost, we find that training this deep generative model, sometimes they require a high compute time on GPU. So the compute cost itself may sometimes be higher than your storage cost. So it's unclear if it's worth it. And the goal for this project is we want to find a way to balance and maximize the trade-off in these three pain points. And PrvTel, in this sense, at a very high level, is we use a very lightweight generative model, which is a variational autoencoder. And we also add noise before we train the model to try to minimize its effect on fidelity. And let's first look at some key insights. The first insight is we really want to be able to keep the data fidelity. So therefore, we decide to add the privacy noise before the training. So here, let's say you have some telemetry features. First, we decide to learn like a Bayesian network on top of your different features. And this part is inspired by a prior work called private Bayes in the differential privacy world. So instead of adding noise independently on each feature at each rows of data, with Bayesian network, we can add noise to their lower dimensional conditional tables. And with this way, that the output data is already privacy preserved, and within private Bayes, they proved that it still maintains the strong privacy guarantee. And then with this privacy preserved data, then we use it to train a lightweight variational autoencoder model. However, we started with the traditional variational autoencoder, and we quickly find out that it doesn't work that well. So here is one figure that's showing the correlation of features between the original data and the synthetic data's difference. So here for these numbers in the squares, the lower, the better it is. Like if it's 0, then that means it's perfectly matching the original data. So then we tried out like different approaches to see how we can improve this part. And then we find out that one way to improve this is we need to actually model this correlation in the variational autoencoder design. So let's say that if we model the covariance metrics in the loss function, and with this way, we can explicitly learn these feature correlations, and we find out that it made this correlation learning part much better compared to just using some strawman or like a simple variational autoencoder structure. And the third insight is we do also need some domain-specific encoding. So with, let's say, continuous data features in your telemetry data, such as like packets, bytes that have a lot of different values, we can treat it as a distribution. However, if you use some standard distribution that, let's say, a Gaussian, it will miss the heavy tail features that exist in our telemetry data. For this part, we decide to use this Gaussian mixture model, which can better capture like different tails and components in the telemetry data distribution. And for the categorical type of data features, for example, with port and protocol, we find out that this prior work used this word-to-vec embedding methods that actually works pretty well. So we adopt their method. Now let's put them together. With the PrvTel system, we have two stages. The first one is data storage, and second is retention query. So at the first stage, with the telemetry data, as I mentioned, we first construct this Bayesian network. And then when the operators set a privacy budget epsilon, then we add the noise into the data before the training. And then we use this data to train this specialized variational autoencoder model, which is a very small model. And then at the storage time, then we only retain the model decoder. Then at the second stage, when the user or the operator have some downstream queries, we use the decoder to regenerate the data and answer those query results. And here's our evaluation setup that we tried with 6 different baselines, including different sketches and different differential privacy-powered generative model approaches. And we also tried with 6 real data sets. We really tried to vary the data set we use, including across different sizes and different features and different durations. And here are some results highlight. That first one is we do find out that PrvTel generated data can have a much better fidelity compared to other differential privacy approach. So here the setting is we set all of the budgets to be same as 2. And then we find that, let's say with x-axis is different features, and y-axis is the distance metric. PrvTel can achieve the best fidelity compared to baselines. So for this part, we do find that like if you consider differential privacy, so when you add noise before the training, it definitely helps you minimize the fidelity degrades in the system. And the second key result is we also find that PrvTel could maintain some downstream task utility too. So if you look at like this 2 metrics, which is forward bytes and forward packets over time, we saw that PrvTel regenerated data. It does like help like recover, or it does capture this pattern that existed in the original data that spiked over that time period. So the reason behind this is the correlation aware design of PrvTel like helped capture these correlations between features. So let's say there's this potential like DDoS attack existed in your data set, then this pattern will show up in different features. And with the correlation-aware design that we better captured those like across different features over time. But do note that in order to capture these temporal patterns, we do need to adjust the model architecture to be able to learn it. And then the third key result is about privacy. So here, let's say we try with different privacy budget and compare PrvTel with different baselines. So when the budget is going up, going higher, which means the privacy is getting looser, you do see the gap between baseline and PrvTel is getting smaller. However, that maybe you can think that why don't we just use a big privacy budget then? Then we tried it out with some membership inference attack. Means that we trained an ML model on top of original data to see if when any specific data point is included in the original data or not. And here we find out that when the epsilon or the privacy budget is big, then the inference attack success rate is very high. It's 100%. And when the budget is small, when it's equal to 2, then the attack success rate is closer to random guessing. So this means that when privacy gets loose, although the fidelity of baseline could increase too, but that also makes the attack success rate much worse. And the last result is about the retention cost over a long time. So I used 2 data sets as example that if you save them for over 5 years, let's say, although at the very beginning, PrvTel might be more expensive than gzip because we still have this computational cost. But when you save it for over a long time, the cost of PrvTel is constant, while the cost of lossless compression, they're growing linearly. So therefore, we are compared to other baselines, we are much cheaper to train and to store over time. And that is the key idea of this project. And if there's two things I want you to remember is first, that if you care about privacy in this case, then do not try to add noise during the training, like if you want the high fidelity. And the second part is the generative model. It can be a generalizable data retention approach, but we need to use it carefully in terms of data architecture, the model architecture design, and the data encoding so that it could be well adapted to our specific domain. And welcome to try out our project at this web link, and please feel free to ping me if you have any questions. Thank you so much.